Have you ever stopped to think about just how complex seemingly simple things are, like making coffee or tidying your room? They feel easy, but if you break them down, it's this whole sequence of tiny steps, right? Decisions, actions. Now think about getting an AI, specifically these big language models, to not just understand that process, but to actually do it. In the real world, how do we make that leap from language to action? Okay, let's unpack this. Today we're diving deep into something pretty fascinating. It's a paper called Language Models as Zero-Shot Planners, Extracting Actionable Knowledge for Embodied Agents. It's really all about exploring how these powerful AI models could maybe start turning their, huge understanding of language into actual physical actions.
Exactly. And for you listening, our mission today is really to dig into this quite remarkable finding. Researchers are trying to see if an LLM, just using its existing language knowledge, can generate a sequence of actions that an agent, like a robot in a simulation, could actually perform. And the really intriguing part, they're doing this without giving it any extra training specifically for planning. It's zero shot.
Zero shot, okay.
Yeah, it's about figuring out if these models just sort of know how to act purely from all the text data they've learned from.
So the paper kicks off with this surprising discovery. What was it that really jumped out about models like GPT-3 or Codex?
Well, what's fascinating here really is just how much knowledge about the world seems to be latent, just sitting there inside these models. The core finding is that if you prompt them the right way, even with zero specific training on planning actions, they can generate these remarkably plausible, high-level plans for pretty complex tasks.
Wow.
And that's the zero-shot planning bit. No examples, no fine-tuning needed for the planning itself. It really suggests this kind of operational know-how is just embedded in their structure from learning language. And what's really key here is that this effect, it seems to really kick in with the larger models. There's a definite link between the model size and this ability.
Right, scale matters. Okay, maybe give us an example, just to picture it.
Sure. So take the task, brush teeth. A smaller model, GPT-2 1.5b, actually came up with something pretty reasonable. It said, 1, walk to bathroom 2, walk to sink 3, find toothbrush 4, pick up toothbrush 5, put toothbrush in mouth 6, move brush around for 2 minutes 7, spit out toothpaste. 8, turn on water, rinse brush. 9, turn off water, return brush to cupboard.
Okay, yeah, that sounds pretty much like how you'd brush your teeth. Quite good.
It does sound good. But then you see where the initial common sense gaps can pop up.
Yeah.
Codex 12b for the same task gave this slightly, humorous suggestion. Step 4, put pot on sink. Step 5, put brush on toothbrush. Step 6, turn to toothpaste. Step 7, put teeth on a toothbrush. Okay, yeah, I see the problem.
Exactly. You can almost picture a robot getting very confused. It shows they have some knowledge, but it's not perfectly, grounded in reality yet. Which brings us right to the critical but. These plans might sound plausible, maybe even clever when we read them, but often they just aren't executable, right? Not in the real world or even in a simulation. So what does that mean for actually getting the task done?
That's the core challenge they hit. So the researchers tested these plans in a simulated environment called virtual home. You can think of it like a detailed virtual house designed specifically to simulate realistic human activities.
Okay.
It works using these basic commands called atomic actions. They have a really strict verb-object syntax, like walk living room 1 or open fridge 1. Very precise.
Got it. Not like natural language at all.
Not at all. And when we talk about whether a plan is correct in this context, it's often judged by humans. Why? Because these tasks are so open-ended, it's incredibly hard to just computationally score them perfectly. This reliance on human judgment really highlights the gap they're trying to bridge. What sounds right to us often isn't specific enough for the machine. That's the tricky part.
So why do these initial plans fail? What are the main reasons they aren't executable?
Well, there are a few key issues. First, the LLM's natural language, like I first walked to the bedroom, just doesn't match virtual home's required walk bedroom format.
It's like a language barrier.
Exactly. It's like speaking English to a system that only understands this very specific code. Second, the model might use words or mention objects the simulation doesn't even know. Like saying microwave the chocolate milk if microwave isn't a possible action or chocolate milk isn't an object in that virtual kitchen.
Right. The environment has limits.
Precisely. And third, you get linguistic ambiguity. The LLM might say open TV, but maybe the system needs the command switch on TV. Subtle, but enough to break the execution.
And the numbers really drive this home, don't they? You mentioned GPT-3 175b.
Yeah, the numbers are stark. Vanilla GPT-3 175b, the big one, Humans judged its plans as almost 78% correct. It makes sense to us.
Pretty high.
Very high. But its actual executability in virtual home, a tiny 7.79%, basically couldn't do anything most of the time.
Wow, that's a huge disconnect.
It really is.
Yeah.
And interestingly, some smaller models sometimes scored higher on executability, but it turned out they were often just, well, ignoring the actual task and repeating whatever example plan they were given in the prompt.
So cheating, essentially. Not really solving the problem.
Exactly. It's a clear failure mode. It tells us that just having the linguistic knowledge, the what and why, in human terms, isn't enough. You need the how in the environment-specific language.
Okay, so we've got these super smart LLMs that can kind of think through a task, but can't actually do it because the instructions aren't right for the machine. So how on earth do you fix that? This is where it gets really interesting, right? The solutions they came up with.
Exactly. And this is the really clever part. They propose 3 key tools, and crucially, all of them work on top of the existing pre-trained LLM. It's frozen.
Meaning they didn't have to retrain the whole massive model.
Correct, which is a huge advantage, saves enormous time and cost. So the first tool is called admissible action parsing by semantic translation. Basically, they take the LLM's free-form natural language step.
Like, go to the kitchen.
Right, and they map it to the most semantically similar action from that huge list of nearly 48,000 valid actions Virtual Home understands.
How do they measure semantically similar?
They use another language model, something like Sentence Roberta, to create embeddings. Think of embeddings as like numerical fingerprints for the meaning of sentences. This lets them compare the LLM's output, like go to the kitchen, with all the valid actions, like walk kitchen, and find the closest match in meaning. It's like a smart translator.
Okay, a meaning translator, not just word for word.
Precisely. The second tool is autoregressive trajectory correction. This one's quite neat. Instead of generating the whole plan and then translating it, they do it step by step.
Interleaving them.
Exactly. The LLM generates one step. That step gets immediately translated into a valid virtual home action. And then here's the key, that translated action gets added back into the prompt for the LLM to generate the next step.
Oh, I see. So the model sees its own translated previous step, keeping it grounded.
Yes. It's autoregressive. It uses its own corrected output to guide the next output. It creates this feedback loop that stops errors from piling up. Much more robust.
Clever. And the third tool?
The third is dynamic example selection for improved knowledge extraction. So usually you give the LLM one fixed example in the prompt to show what kind of output you want. Instead, they dynamically choose the most similar task example from a library of demonstrations.
Based on the current task.
Yes. So if you ask it to apply lotion, instead of maybe showing it an example for make coffee, the system finds a more similar example, maybe shave, from its library. This gives the LLM a more relevant hint, a kind of weak supervision, guiding it towards the right kind of actions for that specific type of task.
That makes a lot of sense. It's like giving it a better starting point each time.
Exactly.
And the beauty of all this, as you said, is it works like smart adapters on top of the existing LLM engine. You don't need to rebuild the engine.
That's the profound implication. We're unlocking the knowledge that's already there and making it practical, usable, without starting from scratch each time. It's about efficiency, bridging that gap.
So did it work? What happened to the executability after they applied these tools?
Oh, the results were dramatic. Huge improvements. Remember those single-digit executability scores?
Yeah, like 8% for GPT-3.
All right, well, translated Codex 12b jumped to 78.57% executability, and translated GPT-3 175b hit 73.05%.
Wow. That's night and day, a massive leap.
Absolutely. But, and this is crucial, there's a fascinating trade-off they observed.
Okay, what's the catch?
The catch, or maybe the dilemma, is highlighted really clearly in their results, like in Figure 1 and Table 1 if you look at the paper. While executability shot way up,
Yes.
human judge correctness sometimes took a noticeable dip. So translated to GPT-3, the big one, went from that initial 78% correctness down to about 66%.
So it became much better at doing things the simulator understood, but the overall plan sometimes made less intuitive sense to a human.
Exactly. It points to this fundamental challenge. How do you balance making an AI follow strict environmental rules perfectly with maintaining its sort of human-like common sense? Making it executable sometimes made it slightly less correct in a broader sense.
Why did that happen? Did they figure out why correctness dropped?
They did look into it. A couple things seemed to be going on. One was that the translation LM sometimes struggled with what they called compounded instructions. Like if the original plan said brush teeth with toothbrush and toothpaste, the translator might have trouble mapping that complex idea onto a single valid atomic action.
Right, it's trying to simplify too much sometimes.
Potentially. Also, sometimes the translated programs would just stop too early. And part of that might actually be limitations in Virtual Home itself. The simulation might not support every single little action needed to perfectly complete a complex task. They even note that human-written plans in Virtual Home are often only considered about 70% complete because of these environment limits.
Okay, so some of the correctness drop might be the environment, not just the translation.
That seems plausible, yeah.
But even with that trade-off, the progress in getting something done, something executable, is huge. Do you have an example of a translated plan that worked well?
Absolutely. Remember the original quirky plans? Well, here's translated GPT-3 175B trying to throw away paper. 1. Walk to home office 2. Walk to table 3. Find table 4. Turn to table 5. Find paper 6. Grab paper 7. Walk to trash can 8. Open trash can 9. Put paper on trash can 10. Close trash can.
Okay, now that sounds like a sequence a robot could actually follow, step by step, using actions the environment probably understands. Much more robust.
Exactly. And there's a metric in Figure 4 that really captures this net improvement. It looks at plans that are both executable and judged correct by humans. This is the sweet spot, right? Real grounding.
Yeah, that seems like the key metric.
And for translated GPT-3, that number jumped from just 6.8% initially to over 35%. So a much higher percentage of plans were now both doable and made sense. A big step in grounded behavior.
And did they test which of those 3 tools was most important?
They did, using ablation studies, basically, taking components out one by one. And the results were clear. The semantic action translation part was by far the single biggest factor in boosting executability.
Got it. Translation is key. What about the length of the plans? Did they just get shorter and simpler?
That's a fair question. People might think the improvement came from just making trivial plans. But Table 5 in the paper shows that's not the case. The translated models generated plans of reasonable length, actually quite comparable to the plans humans write. So they weren't just making them short and incomplete, they were still generating comprehensive sequences.
Okay, that's good to know.
And this connects to another interesting point. What about just giving the LLM detailed instructions?
Instead of a high-level goal.
Right. They tested this too, shown in Table 4. If you give the LLM a very specific step-by-step guide like walk to the office, turn on the light, grab the book, they found the models could generate highly executable programs, with correctness scores getting close to supervised methods, even without any fine-tuning for this.
Wow, so they're naturally pretty good at just following instructions if the instructions are specific enough.
It really seems so. It highlights this inherent instruction-following ability they possess, which is quite impressive.
Okay, so great progress, but I assume there are still limitations, right?
Yeah.
Where does this research point next?
Oh, definitely. And the researchers are very open about them, which is great. First, there's still that drop in correctness for some tasks. That suggests the semantic translation could still be improved. It's not perfect.
Makes sense.
Second, this whole approach focuses on what you might call mid-level grounding. It connects high-level goals like make breakfast to actions like gone milk, open fridge. It doesn't get down to the really low-level sensoromotor stuff like how does the robot hand physically grasp the milk carton? That's a whole other layer of complexity.
Right, the actual physics of movement.
Exactly. And a really big one. These models are essentially operating blind, purely from the text prompt. They have no idea about the current state of the environment. They can't see if the fridge is already open or if, like you said earlier, there's no milk. They can't adapt to real-time feedback. That's a major limitation for real-world application.
Yeah, that seems critical for any real robot.
Absolutely. And finally, just the ongoing challenge of evaluation. How do you accurately measure success for these complex, open-ended tasks? There's no single perfect score, so human judgment remains really important, but also subjective.
So quite a journey then. We went from seeing this surprising latent ability in LLMs to plan actions through the challenge of making those plans actually work to these clever techniques for bridging that gap.
It really is.
Yeah.
And stepping back, connecting this to the bigger picture, this research feels like a really significant step. It demonstrates that these large language models, they aren't just about processing text anymore. Their knowledge can be a foundation for decision-making, for acting purposefully in interactive worlds. It moves us closer to genuinely autonomous embodied AI.
It really shifts the perspective on what these models are capable of. So Thinking about all this, what stands out most to you listening in? Imagine when these systems can take in real-time visual information, feedback from the environment. How might that change everything? How we interact with technology, our homes, maybe even how tasks get done in the future. Lots to think about.